So to see what can be done, how this problem can be solved, let's use Python, and this time let's use Python's graphics. That is, let's try to graph both functions. Which functions? The equation of infinite tetration on one hand, and what should be the general solution? This one. So our first function, which we will see expressed by a red line, is that of infinite tetration. As for the solution would be an x function that gives us an x as a function of k. But since we want to have only two parameters, so we can use a single window and possibly see if the two curves overlap, what we need to do is transfer the k to y, okay? And so we get this function to calculate. Now, this function is not very simple because it is the, let's say, inverse function. That is, in reality, we would need to calculate y as a function of x, and therefore we would need to calculate the inverse function of this function. This is a problem because from an analytical point of view, it is difficult to perform this inversion. However, there exists, and this is also a useful thing to know, a very simple trick that can help us from both a numerical and a graphical point of view. We can perfectly well calculate this function with y equal to x, that is, as if it were a normal function, let's say, with y as a function of x, and then swap the terms when we either visualize the graph or use the data within vectors to use the numerical values we are interested in. So a computational trick that helps us overcome a mathematical problem in this case. So this, you will find this used in this code. This code is used to draw the graph of these two functions. There are also some extra things that I use just to run some tests. Let's look at the main parts of this code. There is a loop of 5,000 steps to print the x. Then the x is derived from the I. What happens? For every x, I then have to calculate the infinite tetration. So I need a second loop inside the x that calculates the infinite tetration for each value. And here you can see a somewhat strange condition. The condition is that the I must be less than a value of 1445. Where does that come from? Well, it comes from this. In the first tests I did, it was noted that as soon as this value of x was exceeded, that is, the value x equals 1.445 corresponds to this, the tetration immediately diverges. So from a completely heuristic point of view, that is, if what comes out of the tests from the calculation, this little number pops up that prevents us from calculating the tetration for higher values. So for purely technical reasons this time, having to fill in the value, otherwise there would be problems with the display, I set the higher values to 0, but obviously this doesn't have any particular meaning, okay? So now we will see a red line that will have a certain trend, and then after a certain, outside of a certain interval, once it exceeds the value of 1.445, it will go to 0. We won't consider that part. After that, you see that I'm just printing these results. If you look closely, there is a difference. While the variable x and the variable y I print in this order, the variable z and the variable x I print in reverse order. Why is this? Because the variable x and the variable z, s, lead me to print the green line. Let me check for a second. Yes, exactly. It's the green line which represents this function. I calculated this function as an inverse, and then I inverted it. I re-inverted it only at the moment of printing. This way, I will have the graph of this function. And we get, now I won't run it, because even if reduced to the minimum, it needs a few minutes to be executed. Let's go directly to the result. We get this graph, which is very simple, but even though it is very simple, it tells us, it already gives us a lot of information. We can already see, for example, confirmation of what I was telling you before. The function of infinite tetration, which is the red line, stops abruptly at a certain value of x that corresponds to that 1.445. I can see this, let's say, from the program's execution, because the program's execution stops at that point and around a y value of approximately 2.7, 2.5, 2.6. I can estimate it better because the window allows me to identify the points. So this already gives me information about the behavior of the function. Then we see that, on the other hand, the function of our solution is quite interesting. Actually, it is clearly defined, even if it does, in fact, go back slightly to a previous state before moving forward again. This means that the behavior of the function is multi-valued, if we use the technical term. So for some values of x, they correspond not to just one value of y, but to two values of y. However, this doesn't really interest us. It doesn't harm us, because we will stop here. Clearly, our function of infinite tetration, let's say, has this limit, and we stop at this limit. Let's observe that the point y is equal to 2.7, so a number that perhaps will remind us of something later. Let's see what happens in the lower part of the function. In the lower part, it would seem, it's hard to see here, we would need to zoom in, but we'll do that now, that there is instead not a perfect correspondence between the two graphs, but a difference between the two graphs. So let's pause for a moment first on the graph, on the upper extreme of this graph. X greater than 0, that is, x must be greater than 1.445, gives us the information that the function of infinite tetration becomes truly infinite. That is, it assumes infinite values, it diverges, and therefore we cannot calculate it. So for the moment, we stop, we reason within this interval, okay? And let's try to interpret this number, which in itself doesn't tell us anything, in the form of the function of the solution we thought of. I mean, we also have this other function, the green function, that overlaps with the red one and has this meaning, this trend k equals 1 over k. So how much can k equal 1 over k be if x in turn is equal to 1.445? Well, it's very simple, the y tells us. The y tells us that value of approximately 2.7. But 2.7, let's say we all remember, is Napier's constant. It's very similar to Napier's constant. As a hypothesis, we can then think of writing this maximum limit as e raised to the power of 1 over e. And now we see it here. We see it here. So we make this hypothesis. From a graphical point of view, it would seem that the maximum limit of the infinite tetration function is this e raised to the power of 1 over e. Let's go see what happens at the minimum limit. At the very minimum limit, let's go ahead and zoom in closely. We are performing a simple zoom of the figure here, and I would like us to take a closer look at this specific point. It is this exact point where the two figures essentially begin to separate from one another. And here we are interested in the x-coordinate. We have a value that I have reported here of 0.065. Let's do more or less the same thing. So the point is, it has these two coordinates, x0 0.065 and x0 0.37. We are essentially interested in this. And we want, since the parameter, the maximum limit we have set in terms of e raised to something, we also set the minimum limit parameter in the same, let's say we use the same order. We can't do e raised to k over 1 over k, but we decide to do e raised to r. So we try to solve this equation because this equation is also simpler to solve. It's enough to calculate the natural logarithm of 0.65, and we get once again 2.72 with a minus sign in front. So in our approximate idea, we can say that this minimum limit could be e raised to minus e. And so in the end, we have an interval, let's say, of values that we can write in this way, using numbers, the numerical values, but using it in a more analytical way. We can write e raised to minus e, and here e raised to 1 over e. Actually, there should also be an equal sign here, because you can see that for this function, even for this value, the function is still defined. There is a small mistake here. So let's move on. So we have this specific interval to work with, and the graph has already told us quite a few important things about the behavior. At this point, we have to ask ourselves, what can we actually do next? to try to understand the situation much more deeply, we can shift our focus and try to find a precise analytical solution to the problem. And by looking for analytical solutions, the equation of infinite tetration, which is parameterized, by the way, is an exponential type equation. If you go looking around a bit, exponential equations can also be solved thanks to a very powerful tool from an analytical point of view called the Lambert function, the Lambert W function. I will call it the Lambert function. How is the Lambert function defined? If I have an equation of this kind, actually here I could also have f of x. It holds more generally f of x times e raised to f of x. If I have a function of this kind, the Lambert function acts as an inverse function. It gives me the x that satisfies this expression. And so the Lambert function is defined in this way. This too, let's say, is a bit strange because we don't have a simple analytical form to be able to express this function. We know, however, that if this expression is valid, then we can define x as the Lambert function of y. Obviously, this helps us a lot because we can very well, as usual, draw the graph, calculate this function from a numerical point of view. If you go and look on Wikipedia, I got this information from Wikipedia, specifically on the page where they talk about the Lambert function. You can see, for example, what the graph of the function looks like. It's a somewhat peculiar graph because this is also a multi-valued function. However, we aren't actually interested in the multi-valued part of the function. We are interested in the part where x is greater than 0. And to calculate the values, assuming there was a need, we could also use the technique I mentioned to you just a moment ago before. So in the end, we are interested from an analytical point of view because we finally want to solve our infinite tetration equation from an analytical point of view. As a first step, what can we do? As a first step, let's try to find a different form for the infinite tetration. So we are not working on the equation yet. We are just working on the tetration itself. And we write it in this form using a step that is quite common. So if I decide to use exponentiation, specifically e raised to the power of the natural logarithm of something, well, this value x can actually be rewritten in this particular way. Let me show you how that works. Obviously, in reality, I must be sure that this, what I write inside the natural logarithm, is a number, is a finite quantity. So this is a problem that we must not, let's say we must not forget, but we will see it now. Let's take for granted for a moment that this is valid. We will talk about it in a moment. Having done this hypothesis. So in any case, we remain, the graph helps us from this point of view, we remain within that interval that I told you about, and we can certainly make this substitution. We can also move on to this other value. What have we done? We did the same thing we did in the first video. That is, we considered all the exponentiations except the first one, and we extracted them using the properties of the logarithm, and we put them to multiply. Attention, we are also assuming here, however, that this chain of exponentiations, which derives from the general one, let's say excluding the first one, is still, since it is infinite, equal to this one. So we didn't make a distinction. We don't make distinctions between this expression and this expression. Okay. So what happens? We have this logarithm. We consider these exponentiations, we pull them out of the logarithm as multiplication. It's the logarithm rule. We remember that x must be greater than 0, but we said that we are working in an even narrower interval that satisfies this condition. So it's fine, we can move on. To isolate the infinite tetration, we move this term to the first member, so we divide both members by e raised to minus the logarithm of the tetration multiplied by the natural logarithm of x. And so this that we have here, in other words, moves to the first member with the sign changed. And here we get 1, and here we have this expression. Now, what is the problem? How do you use the Lambert function? We must obtain an expression on one side of the equation where we have x or actually a function of x times e raised to the same function. So we need to obtain this form. Let's look at where we are here. We have the tetration here, and we are missing the minus natural logarithm of x. So what we can do is multiply both sides by minus natural logarithm of x. Here too, we must be careful about one thing. When we multiply both sides of an equation by the same number, we must be careful that it is not 0. And so in this case, with the logarithm, we must be careful that x is not 1. So all our previous reasoning holds for x not equal to 1, which falls within the interval of interest. However, we can go and see in this, even in this case, the graph helps us immediately that the value x equals 1 is, let's say, a value where the two functions are equal. We can also verify numerically, it's very simple, that x raised to the power of itself, even to infinity, is always 1. And k raised, that is x equals k, raised to 1 over k with k equal to 1 is always 1. So it's not a problem. Let's say we can verify point by point that the solution is correct. So this problem isn't a problem. We can move on. That said, we have this form minus the logarithm of x. We have this function. And with respect to what we wrote up here, our x will be this, okay? Which we then find also obviously as an exponent of the exponential, and this will be our y. So we can now write this expression. The x is this, and the y goes inside the Lambert function. Okay? The result we get is this. The Lambert function is known numerically, so we could calculate and see, for example, if the numbers are the same as those we calculated in the graph to obtain the graph. This is something that could be done, but I'll tell you right away that I am quite confident that this is true. Let's observe, however, that what we have done is nothing more than finding a new format for infinite tetration. That is, we have put the infinite tetration into a different form. We haven't solved the equation yet. We just said this form is equal to this form. It's a different way to express infinite tetration. Let's note, the first thing I already showed you, that we still use that reasoning whereby an element extracted from an infinite set of identical elements does not change the value, the initial set. We used it again, okay? And the question mark we left earlier remains regarding the fact that this substitution can only be done if x is finite. Therefore, the finiteness of the Lambert function, at least in a certain interval, is an important thing that we must prove. And here, in a sense, we give up, because this is too complex a topic. But none other than Euler comes to our aid, and Euler proved that infinite tetration is convergent, and it is convergent in the exact interval we found previously. We found it graphically in a clearly very approximate and imprecise way. But knowing, let's say, that the solution would have been this, it wasn't impossible to trace back to this interval identified by none other than Euler, one of the greatest mathematicians in history. So we can all agree that at this point we are now able to write out the infinite tetration function using this Lambert function. And we are looking at this within this specific interval right here, where, by the way, we previously observed that our equation had, in our professional opinion, this particular type of solution. It is quite interesting to see how these components align within this defined range. Now, to test if this